Okay, so thanks to still be here, to still be willing to pursue these lectures on turbulence. So today, I guess I will be less terroristic than yesterday, and I will talk about simpler problems. And so the thing that the applications that are motivating what I'm going to talk about today are basically situations where you have spaces which are transported by a turbulent flow. So and typically when these spaces are passive in the sense that they don't have any feedback on the flow. Okay, so there are different cases which are motivating to get such a description. So one case is the formation of planets in protoplanetary disks. So I guess you know that a star is forming after the collapse of a nebula, so gravitational collapse of a nebula. And typically, so you are creating a star with a gravitational collapse, and then a part of the dust and gas which was making up this nebula is still not accreted by the star, and start to migrate to a plane, to the equatorial plane. And then in this mix of dust and gas, basically, so gas is in the turbulent state, dust is transported by the gas, and dust will tend to form some aggregates, which are planetary embryos or planetesimals, which will then grow to create planets. So basically, there is a very large community of astrophysicists which are trying to quantify the timescales at which you're creating the planets this way. So then, of course, there are many industrial applications, including sprays, injection in engines, things like that, where typically you are pouring some mix of gas and droplets, and then you want to optimize the combustion of these droplets, which are going to evaporate. So you want them to evaporate quickly and to mix well with the oxygen which is inside the air in order to optimize combustion. So that's another place where you need really to understand at which velocities you are mixing things or concentrating things. Then there are many applications related to plankton dynamics in oceanology, where typically you want to understand how different species of plankton. So plankton has almost no, at large scale, plankton has almost no active behavior. So it's not really swimming in order to detach from a large scale eddy in the ocean. So it's swimming only at small scales. But then still you have things which are like plankton blooms, where you have dynamical effects which are very important in order to get right mixing between the transported plankton and the nutriments which are going to make the plankton bloom. Okay, and then so of course the transport of sediments, which can be quite important again for in the oceans, and so the formation of clouds and basically the dynamics inside clouds, where you have droplets which again are very, very small, so which are almost following the flow and which are mixed with the ambient air. So you want to understand the rate at which they are mixed, the rate at which they detach from moist regions, how this is mixed with dry region of air, etc. So that in order to understand the growth rate of the droplets and the typical lifetime of clouds. And then so I think I will not talk much about fibers because this is a bit more complicated. So then you can imagine also to have transported species which are not just microscopic things, but which have, for instance, a long direction in one dimension, and for which then you have to understand how the gradients of the flow, the different velocities increments that you can get in the flow are affecting the conformation of such fibers, whether they are going to be folded, stretched, if they are going to tie up together, etc. So now, basically, I will start with the basics. So now, I'm going to start with the most simplest case, the case where you're considering a field which is just transported by the flow. Okay, so assume that you have a fluid velocity which is prescribed, which is a solution to the Navier-Stokes, as we have seen, which is in a turbulent state, and then we are considering the advection diffusion equation for a scalar field theta, which could be, I don't know, the temperature, the concentration of something, and which is just advected with this prescribed velocity field. Okay, so you have these two terms, the term advection and diffusion. So that so the usual name for such a quantity is a passive scalar, in the sense that it's passive because the theta field is not affecting you. Okay, so you could think about active fields. So I mean, it's the jargon is a bit different from active matters, of course. So active fields will be a field which has an effect on the velocity. So for instance, if you think about temperature while you're considering convection effects, okay, so then the temperature is an active field. So now there is something which is very easy to obtain here is to understand the ratio between these two scales. Okay. So between these two terms, I'm sorry, the advection term and the diffusion term, and by looking at this ratio and looking at what's happening at very small scale, you can define what is called the bachelor scale, which is somehow the equivalent of the Kolmogorov dissipative scale, but for the diffusion equation. So typically this bachelor scale, so it's proportional to the Kolmogorov dissipative scale and to the ratio between the diffusivity and the viscosity of the fluid. Okay, so this is usually called the Prandtl or the Peclet number. Okay. So this bachelor scale is telling you the following thing, is that if you're looking at scales below this bachelor scale, diffusion is dominating. Okay, so this term here will become very important. While if you are above this bachelor scale, advection is the most important effect. So now if we look at some numbers to get an idea of what will be this bachelor scale. So in the atmosphere, the typical value of the Kolmogorov scale is of the order of 1 centimeter. That's the typical value. Yes? Nu is the fluid kinematic viscosity. So if you okay, so basically here, in order to do that, so what I do is that I non-dimensionalize this equation at the dissipative scale of the fluid flow. Okay, so which means that I'm rescaling scale by eta. Okay, and so eta is now my scale, which is order unity in my rescale system, and then I in order to compute to put out a time scale, I'm using the fluid kinematic viscosity. Okay, so that then I have a space and time scale, or space and velocity scale. And once I have rescaled everything, then here I will get some number which is the ratio between LB and eta. Okay, so that's how you get it. So now, so what I was saying is that in the atmosphere, so if we take the example of the atmosphere, for which the typical Kolmogorov scale is of the order of 1 centimeter, okay, in a turbulent air, I mean. So then you look at the diffusion of ozone, for instance. So ozone is quite important because you need to have models for the diffusion of ozone in order to monitor pollution, okay, because ozone is important for pollution. So basically, you have this value for the diffusivity, and when you put typically the numbers here, what you get is that the bachelor scale is 0.8 times the Kolmogorov scale. So which means that it's just a bit smaller. Okay, so that if you want to monitor pollution, so your typical scales are, I don't know, kilometers. So basically, it's well above that. So diffusive effect will have no contribution. Okay, everything will be described by the advection term. Okay, so now same. So now you take something which is even less diffusive, like an aerosol, so a small dust particle. So now diffusivity, you see, is much smaller, and you see that the bachelor scale is of the order of a micrometer, and so which means that the bachelor scale is of the same order as the size of the aerosol, so which means that, except if you are looking at microscopic things, no effect of diffusion. Okay, so this is to tell you that when you are looking at applications of turbulent transport, usually basically the diffusion is not contributing at all to the mixing of the scalar, but everything is entailed in the advection term. So how do we try to understand that? So now you have already certainly heard about that. So the first idea to try to model the effect of the advection is to introduce an effective diffusion by the flow, which is called turbulent diffusion. And I will show you a bit how this works. So assume that you have your equation like that. Okay, so the advection diffusion. You have a given initial data. Okay, so basically you can interpret this equation as a Fokker-Planck equation, if you want, associated to the following dynamics. So assume that you are taking tracers. So tracers are just advected by the flow. Okay, so they are just a solution to this equation, to which you are adding some noise with an amplitude, with a variance which is 2 kappa. Okay. And so now you can by looking at such stochastic trajectories. So now you have a stochastic ensemble of trajectories for different realizations of the diffusivity, the diffusion. So you can reformulate the solution to this equation as in this way, as an average over these different trajectories corresponding to different noise of the initial value of the scalar of this theta 0 computed at the initial position of these trajectories. So let me, I mean, the sketch is easier to understand. So you start from your final time. Okay, so you want to know the value of the scalar at a given position x at time t. So you start from this xt. You look at all the trajectories of this system, so with this prescribed final condition. Okay, so then you go up to the initial time. Along all this trajectory, you have different initial positions, at which you compute the initial value of the scalar field. And then by doing the average of this initial value over all these different paths, then you get the final value of the field. Okay, so this is the usual Lagrangian approach to understand this advection diffusion equation. So you have to think of the backward integration of the trajectories. Okay, so you have to integrate backward the trajectories, perturb them with noise due to diffusion, and then make an average over this noise. So now what's the idea? So the idea is to try to interpret the effect of this velocity as a diffusion itself. Okay, so to say, let me look at timescales which are much longer than the correlation time of this velocity, so that I can model this thing as here yet another effective diffusion. Okay, so how one is doing that? So it's work which is done to Taylor in the 20s. Yes, please, Abhishek.
So you evolve back to time 0.
Yes.
And then you get the distribution of theta at time 0.
Yes,
so,
exactly.
So how do you ensure that you get back the initial theta?
No. So basically, the theta 0 of x is a function which is prescribed on this line.
Right. Yeah.
Okay.
Yeah.
So it's just the initial value problem.
But, you're doing this backward in time. Right?
Yes, exactly.
So how do you know that the initial will be you'll get back the?
So in order to construct the solution at time t, so somehow if I didn't have this,
yeah.
Okay, so basically this will mean that theta is just conserved along the tracers.
Yeah.
So if you want to know the value here, you need to know where the tracer was coming from.
Right, yeah.
Okay,
yeah.
So now the effect of diffusion is just to add this.
Right, yeah. No, but my question is like, I thought you want to, if I want to solve that initial value problem.
Yes.
With a given u.
Yes.
Then what is the strategy? I didn't understand.
So the strategy. So u is given. Okay.
Yeah.
So I want to know the solution at position x at time t.
Right, yeah.
Okay. So then I construct all the backward trajectories which are ending up at time t at the position x.
Yeah.
Okay, which are solving this thing.
Right.
Okay, so I go backward in time. and I stop at time 0. Then at time 0, I have different position, all these x0s, okay, which are you have an ensemble of x0 corresponding to the different realizations of eta.
Okay.
And then for all these x0s, you know the initial value. You know the initial theta.
Right, yeah.
Okay, so then you make an average over this initial theta by fixing the velocity. That's clear? Or?
Yeah, maybe you have to think. I'll think.
So you will see tomorrow that the way you construct solutions to the Burger's equation is very similar. Yeah. So now, so let me move now to what is turbulent diffusion. So turbulent diffusion. So these ideas are dating back from seminal work by Taylor in the 20s, and then for by statistical physicists, I mean this is known as the Green-Kubo formula. So from time to time it's called Taylor-Green-Kubo. In this equation, the U is prescribed. U is prescribed. Okay, I will talk later about the fact that how to make U a turbulent field. At the moment, we just assume that U is prescribed, that the solution to dx dt equal U are well defined. So now, this Taylor-Green-Kubo formula is using the following thing: is you say that you want to compute the displacement of these trajectories, the mean square displacement of this trajectory solution to this stuff here. Okay, so basically the displacement x of t minus x of 0 is nothing but the time integral of this thing along the tracer path. So this time integral, since you have a square, so basically you have the square of the time integral that you write as a double time integral. Okay, so you have a double time integral from 0 to t of the correlation of the velocity field along, so it's the Lagrangian correlation, time correlation, so along the path. And then, so since you assume that U and eta are independent from each other, basically you have another contribution which is coming from diffusion here. Okay, and now here you see it's like a time integral of a correlation, double time integral of a correlation. So that basically, if you assume that U is stationary, okay, you can write this integral with respect to S and S prime as an integral with respect to S minus S prime and S, for instance. Then this thing doesn't depend on the reference time; it's just depending on the time lag. So you have a first integral which is just giving you a t factor, and the second integral which is giving you the integral correlation time. Okay, so at the end you have maybe you need an extra thing in between these two stuff, no? So basically you have something like a double time integral of the correlation computed at t minus, so at S minus S prime, so ds prime. Okay, so here I just rewrote this thing by writing that the correlation just depends on the time difference. That's okay?
Divergence of U is 0, right?
I'm sorry?
Divergence of U is 0, right?
Average of U is 0, yes. I'm assuming that average of U is 0.
Not average of U. I mean the divergence.
I'm sorry?
Divergence.
And divergence of U is 0 also, yes. So here I think it's not very important, the divergence of U. Here, neither here. Here it's not important, divergence of U. But it's then if U is compressible, still this backward thing is valid only to solve this equation written with U dot grad theta. If you want to consider a density in a compressible flow, so if you want to put divergence of U theta, then it's not backward, it has to be forward. It's the same thing between backward and forward Kolmogorov equations. So let me turn back to that. So basically here, so this is here I just wrote again this term here, and so now since you have, so basically you can write it. So I don't ever remember. I think that you write it as twice times the integral from 0 to t and 0 to s of something like c of tau d tau ds, something of this kind. Okay. Then you can shift the two integrals, and if you shift the two integrals, so what you get is 2 times integral from 0 to t of c of tau d tau times integral from 0 to t of just ds. Okay, and you see, so this is giving you, so this is just t, and then this thing you approximate it. So now it's an approximation as the integral from 0 to infinity of c of tau d tau. Okay, and this is nothing but 2 tau by definition u square times the integral time. Okay, so TL, I'm sorry, TL here is defined as the integral correlation time. So it's the integral of the correlation divided by the variance. Okay, so this is just what I wrote here. Oops. This is just what I wrote here, this part. Okay. And now, so this quantity, this thing here, is what we call the turbulent diffusivity. This is an effective diffusivity that most people working on applications of mixing are using in order to model the large-scale dispersion. So now, so this leads to this kind of mean field description of the dynamics of the average concentration. So now the average concentration, you can approximate it as the solution to this kind of equation, to just the diffusion equation.
Diffusivity, this turbulent diffusivity, it will depend on this energy of the flow of the underlying fluid.
Yes, exactly.
So it will depend on the energy.
So this will be the amplitude, the RMS. I mean the energy of the turbulent fluctuations.
Okay.
This depends on the time scales of your flow, of course, but it's a Lagrangian time scale. That's why there is a L. And basically, the more turbulent energy you have, the bigger is your effective diffusivity. Okay. And so now to come back to your question, so if there is a mean velocity, so did I write it here? If there is a mean velocity, then the equation can be written this way. So it's not very difficult to show it. So now you have an extra term, which is the diffusion by the mean flow. Okay, and you can also put a source of scalar. So why looking at these equations? Because this is typically the equation which is used in order to look at how a plume of pollutant, so coming, for instance, from the chimney of a factory, is diffusing and advected by the wind in order to estimate mean concentration fields. Okay, so now let's assume that the mean flow is just a given constant velocity in the direction x, that the input of scalar is just a point source, a continuous point source. Okay, and so now here you have a very simple advection diffusion equation that you can solve analytically. Okay, but in terms of green functions of the diffusion operator. And basically, then the mean velocity that you get is what is called the Gaussian plume. So it's basically the thing which is used by atmospheric physicists in order to monitor pollution. So this Gaussian plume. So basically, it's a Gaussian in the directions which are transverse to the mean flow. So you see, for a fixed x, so x is the direction of the mean flow. So for fixed x, you have a Gaussian profile, and the variance of this Gaussian depends on x itself.
So here theta is like the density of the plume, or
I'm sorry?
This theta is like the density of the plume or smoke.
It's the mean concentration, yes. It's the mean concentration that you get if your plume is, if your source is emitting in a continuous manner. Okay. So now, if you make the following experiment, so this is just a stupid simulation where you have an input of a pollutant here, okay, with this continuous source. I'm sorry. It's more what? I'm sorry. Yes, so kappa, yes, of course. So I mean, yes, so it's plus kappa here. But kappa is negligible. You know. So yes, indeed, here it would be. So it's the full diffusivity. So I don't know. It depends what you call. Yeah, it could be that this you call it turbulent diffusivity, and then you call the effective diffusivity the sum of turbulent and kappa. So maybe this is my mistake. So now, so this is just a simple 2D simulation. Okay, so I will not talk much about 2D, but just so it's easy to visualize. So for which you have a source which is here, you have a mean flow to the right. So the color background here is this mean profile. Okay, and what is shown as black dots is the instantaneous distribution of your tracers which are emitted from this source. Okay, so what you see is that indeed you can imagine that the mean will be well resolved by this color stuff. But now, if you look at the instantaneous and local distribution, what you see is that you have places where you expect a pretty large density which are completely empty. And conversely, you have places where you expect not much density with blobs of particles. Okay, so which means that fluctuations are very strong. I mean, the deviation between the mean and the actual distribution is very, very large. So if you want, for instance, if in your pollution problem you don't want to know the mean, but you rather want to know what's the probability that in a given place here, because I'm going to construct a house or a school. So you're constructing a school here, and you want to know the probability that the concentration of pollution is exceeding a threshold. Of course, you won't get anything from the mean. Okay.
So for the tracer dynamics, you put some fluctuating field, which is a solution of Navier-Stokes.
Yeah, exactly. So here I'm integrating Navier-Stokes, and then I'm just solving the equation for tracers. This one. And these are different. So it's at the same time different locations of particles of tracers which were emitted at different times at the source. Okay. And the other thing, of course, which is clear, is that now if you look at the spatial organization, it's clear that since you have blobs, you have things which are, you have structures of concentrations which are spanning different scales. Okay, so what is clear is that the correlations of the density are clearly not trivial. That's, the mean is something, but the correlations are really non-trivial. Okay, so let's move on. So I've just tried to tell you is that so turbulent diffusion can be modeled in this way. Okay, so that you have something where you have a large time scales times the typical amplitude of the turbulent fluctuations, that of course, so turbulence is so as you were saying, turbulence is indeed increasing this diffusion coefficient, so decreasing the time scales of mixing, of course. And typically, so you can imagine this picture at a phenomenological level is that if you consider a particle which is diffusing in a set of so you imagine that you have different molecules like that, and you look at how one is diffusing by collisions, then this is more or less the same as saying that you have a particle in the flow which is jumping from one eddy to the other, etc., and we start to diffuse. But of course, the thing which is very important is that this will be true only if we look at very long time scales. Okay, because somehow here what we have done is that here we have approximated this time integral of the correlation by something which that we integrated up to infinity, which means that we need to make this approximation, we need time to be much larger than any time scale that are characterizing the correlation. Okay, so we need to be really above, I mean, after any correlation of the flow.
So this capital TL is the time at which the kind of Lagrangian velocity
decorrelates. Exactly. So now, so the second question is that, as I was telling you, is that fluctuations are not quantified by this mean field approach. That if you have things which are not exactly following the flow, it makes the discussion much more complicated. And then that basically, if you have correlations there is no handle on the correlations between different trajectories. Again, and so for instance, correlation between different trajectories or between 2 points is pretty important. For instance, if you have chemical reactions, because if you have chemical reactions, you don't care about knowing where you can find a particle. You want to know where you can find two particles which are going to react together. So in order, or same if you have collisions. So in order to quantify these things, you need the correlations. And so now, so to address all these points, so basically what we need is we need to understand what's the effect of the Rossness of the fluid flow, so of the fact that actually that there are some special correlations of turbulent velocity fields that we need to model somewhere. That typically the dispersion is not. I mean, the turbulent dispersion is not well approximated by diffusion, and it's showing non-Gaussian statistics. And then, of course, that you have a long correlation along trajectories. So if this correlation was decreasing very quickly, everything will be fine. See, if the typical correlation time would be of the order of the smallest active scale we have in the flow, then, I mean, this diffusive approach will be very good. But the problem is that we have, in turbulence, we have long-range correlations, as I showed you yesterday, so that basically you really need to make this approximation to look at very, 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 very long times. Okay. So now let me move a bit forward. So now let's consider let's try to understand what can be said about the fluctuation of the spatial scalar. So I'm going back to the equation, the advection diffusion equation, this time with forcing. Okay, so why putting forcing is since this term is a dissipative term, I just put an input of scalar so that at the end I can get a statistical steady state. Okay. So now, yes, I'm sorry. So U is fluctuating, but still, so if you look at the budget, so what would be the energy of scalar is just the average of theta square. If you want the spatial integral of this scalar field squared and time average, ensemble average. So if you do this energy budget, basically this term doesn't contribute, it's conserving energy. So somehow, yes, maybe I can write it. So I'm just taking this equation. Okay, I take this equation. I multiply by theta. and I take a space integral. So so basically, I take these equations, U or V, U. Then I multiply by theta, and I integrate with respect to space. Okay. So here what I get is this thing. Agree? Then this term, I will write it this way. So I have theta, ui, di, theta. So this term is theta. And then the work. Okay? So now I'm using spatial homogeneity. So assume that, for instance, that I'm living in a periodic domain, so that I can make integration by parts here without any boundary terms, and don't get any boundary terms. So I just integrate by parts. So let me first rewrite it this way. Okay. I integrate by parts, which means that I have minus di ui of theta square. Okay. And so now if my flow is incompressible, this is 0. So this term is conserving energy. Okay. So same here. Here I'm again doing integration by parts, so that I can write it as minus kappa integral of gradient of theta squared, which means that now I control the sign. So this is negative. Okay. So now so this is what you get there. So in your energy budgets, you have two terms, a dissipative term, which is a bit like the dissipation we had in Navier-Stokes, which is signed, okay, and an input of energy. So now if we look at long time steady state, statistical steady state, etc., for which we expect this to be 0. Okay, so what we get is just an equilibrium between input of scalar and dissipation of scalar.
This is supposed to be positive, right? Epsilon theta.
What? Sorry?
Epsilon theta equals to this. This is supposed to be positive, right?
Which one? This?
Yeah.
It's I'm sorry, yes. It's yes, it's a mistake. It's plus here.
Why is theta squared the energy density? I thought theta was like a density field.
Theta is like, it's not a real density. It's more like a temperature.
But why square? I mean, theta square. Why is that the energy?
Why is it the energy?
Energy density. Yeah.
So it's an abuse of language to call it energy.
Okay,
it's the energy of fluctuations, if you want. If the energy of the scalar fluctuations. But if you want, it's called an energy just because if you put diffusivity to 0 and forcing to 0, then this theta squared is conserved. But like any power of theta. Okay. So that's why it's called energy. It's called the scalar energy. That's just it's jargon. I guess it's turbulent jargon. So now, so now we can work a bit more with this equation, and like in the case of Navier-Stokes, we can look at 2-point things. Okay, so we can compute this equation at point x, multiply it by theta at point x plus r, add to it the same equation computed at x plus r, multiplied by theta at point x. Okay, so the same trick as the Karman-Haworth equation for Navier-Stokes. So what we get there is by doing that is what is called Yaglom's relation, which is then assuming that you're in a steady state, that you're homogeneous, isotropic, the details, which is the same thing as the Forfy flow that we were having for the velocity field, but this time for the advection of the scalar field. So it's you see now it's involving a mixed structure function. So it's the square increment of theta times the longitudinal increment of velocity. And this thing has to be minus this epsilon times r. Okay. I'm sorry, here it should be r, not eta. So in the inertial range of the scalar, we have to have this relationship. Okay. So now, of course, if you say that U is turbulent, so you expect, so you assume K41 theory, Kolmogorov 1941. So you say that delta RU is like R to the 1/3. Then you see that phenomenologically, what this is telling you is that certainly the increment of the scalar is again having the same kind of scaling as the velocity increment. Like delta theta will itself be like R to the 1/3. You agree? So if you say that delta theta is like R to the alpha, here you have R to the 2 alpha plus 1/3, and this has to be like R, and this is giving you alpha equal to 1/3. Okay, so this is the self-similar version of the scalar field. Okay. So now, like in the case of turbulence, so like in the case of the velocity field, of course it's not the case. It's not that simple. And so now, if you look at structure functions of any order, they again have anomalous scaling exponents. And basically, these anomalous exponents are not those that are obtained by the phenomenological arguments. They are shown on this picture as a function of order. And so just to remind you, so this Q/3 is the self-similar scaling, is Kolmogorov 1941. The small dots that you see here, the small black dots, black triangles, are the exponents of the velocity structure functions, the one you measure from the turbulent flow. And then the color things here are things which are measured for the passive scalar. So what you see is that the passive scalar is much more intermittent than the velocity field. Okay, so now the deviations are clear. So of course, for Q equal 3 now, you don't, so you remember that for Q equal 3, for the velocity field, we were exactly sticking to 1 because of the Forfy flow. So now for the passive scalar, for Q equal to 3, you are no more at 1 because the exact relation is not for delta theta to the 3, but the exact relation, remember, is for this mixed thing. Okay. So now the thing which is a bit magical with this passive scalar is that actually this intermittency, the fact that you have scaling exponents which are not predicted by dimensional analysis or by simple self-similar arguments, is true even if the fluid velocity field that you remember we just prescribed has no intermittency. So assume now that you put a model velocity field which has exactly the Kolmogorov 1941 scaling properties, that you solve the advection diffusion equation with this prescribed velocity field, then still the scalar field will show this intermittent exponent. Okay, so this was done for what is called the Crichton model. So what is the Crichton model? So let me write it. So Crichton model is, you think about this equation, and this time you prescribe this velocity field as a Gaussian with mean zero. So it's a Gaussian process, a Gaussian field. So it's mean zero and correlations which are having the right scaling property. So just something like u of xt prime. So this is some function of x minus x prime. So it's white noise in time. Okay. And now you say that this thing is something like, so how you write it? So write it as a constant minus so du0 d1 times x minus x prime to some power. Okay, so it will have exactly the scaling properties which are prescribed by this exponent alpha. So of course it's a tensor. Okay. So it will have scaling properties which are exact, which are prescribed by this alpha. Alpha, you should choose it less than 2, so that you have a Roth velocity field. And now, in this case, basically, this equation, so which is becoming a stochastic PDE, is solvable because you have a Gaussian thing, etc. So this is called Crichton model. Maybe I'm talking about it later. I told you Crichton was a student of Einstein. Remember. So basically, for this model, you can solve it. You can solve any correlation of theta. You can write it as a solution to a kind of Fokker-Planck equation. And then what you can show is that so you have operators which are propagating nth order correlations. Okay, and what you can show is that so in the steady state, this propagator which are so yes, let me write it. So basically, the endpoint correlation is a solution. You can write it as a solution to some linear operator like that. Okay, so it's linear, so it's what can solve it. It's linear, but the spatial dependence is a bit weird because of this alpha here. Okay, so it looks a bit like the propagators of Bessel processes. And so now
so
what you can do? I'm sorry.
The CN correlators involve theta, right?
Yeah. So it's yeah, what I call CN is this. And this operator acts on all these x1, xn. So of course you can assume isotropy, homogeneity to simplify it. But what at the end you can show is that there are some preserved quantity which are called the zero modes, which are actually zero modes of this operator. Okay, which are solution which are inside the kernel of the operator, which are such that ln times this thing is 0. And they look like this. So they look like some power of the size of your endpoints here times a function which depends only on the shape of how you put these endpoints. And the power that you have here is exactly the same as the power that you get here. Okay, and this power depends non-trivially on the order. So I'm sorry, here I wrote Q, and here it's N, so it should be Q. Okay, so this is the work of all these people to show that you have this zero mode. So it's things, so combinations, you see statistical quantities which are preserved by the dynamics. Okay, so it's average which are preserved. So it's like statistical conservation laws. Okay, which have this non-trivial thing. So basically, depending on the size to some power. So the size is typically the how big is your set of points and the shape it has. Okay. And this, yes. R is, yeah, so R is, because you're assuming isotropy, so what I called Ri is xi minus x1, for instance. So it's distances because you're assuming homogeneity. Okay, so what is important? So I don't have time to go into the details of these things, of course, because it's complicated calculations. But what is important is that the thing which is essential here is the fact that the Lagrangian flow is not unique. Okay, it's the fact that here, since you're putting some weird exponent, okay, your velocity field is non-differentiable, is not Lipschitz actually in space, so that trajectories are non-unique. Okay, and now I will focus more on this problem of non-uniqueness. So here, so let me rephrase a bit. So what? Yeah, I'm sorry. So before going to non-uniqueness, let me talk about something else. So which is let's just focus on 2 point things. Okay. So now let's assume that you want to compute the correlation of the scalar at 2 different points. So now the correlation of the scalar at 2 different points, basically you can remember each theta, I can write it through the integration backward in time of my tracers, okay, for different realization of my noise. And then, so which means that the correlation at time t, I can express it as the initial correlation between 2 points, x10, x20, that I weight with the probability of starting from, finishing at x and x plus r at time t. I was initially at x10, x20. Okay, so this is the 2 point probability transition probability. Agree that this formula is fine? Yes.
Without the phi, is it?
Yes.
Phi,
Yeah. Yes.
Without the forcing field, no.
Yeah. Yes. I'm back without the forcing. Indeed. Yes. Indeed. But if I had forcing, it will just add some extra term.
Because with the forcing, you
Yes.
still have the Langevin.
Yes.
That,
Yes.
it will change, right? The Langevin.
So with the forcing, here instead of having that, I have just that dt of theta along my path is the forcing. Okay, so I have that theta of x is that plus the time integral of forcing. And now if you put white noise for the time integral of forcing, then it's easy because it's independent of where you compute it. So basically, why this slide? This slide is to motivate the fact that at the end, you see, it's clear from looking at correlations, so 2 points or more than 2 points correlations of the scalar, that basically in order to understand them, you need to understand transition probability of a set of points. Okay, so this is clear for 2 points. So for 2 points, there is something which is pretty clear, is that now non-uniqueness can be really expressed in a very clear manner. So assume that we are considering such a solution. So forget about diffusivity for the moment. So we are considering solutions to that. And then what we know is that typically the spatial variations of our velocity fields, they behave like a power of the separation, like that, where h in our turbulent case is of the order of 1/3. Okay? It's the scaling that we have for turbulent flow. And this 1/3, which is less than 1, means that the right-hand side of this equation is not Lipschitz. And so if it's not Lipschitz, we don't have unicity of the solutions. Okay? This is clear that not Lipschitz means non-unique. This is clear to everybody? Or we can take a very simple example. The very simple example is the following. Let's look at this equation. dx dt or dr dt is r to the 1/3. Okay, and with the following initial condition. Basically, we start at the place where it's singular. So this equation is singular at r equal to 0. Okay, so then there is a first solution, which is r remains 0 at all times. Okay, and then there is another solution, which is r of t is some constant times t to the 3/2. Okay, so you see that. So I mean, the constant depends. I mean, it's a numerical factor. So here, if you take the derivative of t to the 3/2, you get t to the 1/2. Okay, and the power 1/3 of t to the 3/2 is t to the 1/2. So the constant is just to match. So the constant will be. So here you have c 1/3 t to the 3/2 should be equal to c times 3/2 t to the I'm sorry 1/2. It's not 1/3. 3 1/2. Yes. Okay, so c to the 2/3 is equal to 2/3. So you see that, I mean, clearly you have two solutions, two possible solutions, non-uniqueness. So now this thing, so basically this is typically how a trajectory, ensemble of trajectory will look like. And so now, even if you add diffusion here, okay, so assume that you are adding diffusion. So diffusion is magic because it's smoothing everything. So now, for a given value of the diffusion, you have a unique solution. So you can solve everything. You can write the probability of having starting from two different positions, you arrive somewhere. Okay, and now so once you have written this probability transition, you can make both diffusivity to 0 and somehow also viscosity to 0 in the sense that, or if you want to, you make the thing rose up to the smallest case. Okay, and what you get is that the probability of finishing in two different places at time t, while you have started at the same place at time 0, is different from a delta function. So which means that you have a trace of this non-uniqueness in the transition probability. Okay, so if you want, when you have trajectories like that, you have a finite probability that the trajectories come together, stay at the same place for some time, and then move apart from each other. So this phenomena is what is now coined as a spontaneous stochasticity. So in the sense that even if you have made diffusion to 0, if your flow is not Lipschitz, you still have a manner for the trajectory to spontaneously separate from each other. Of course, all of that by still satisfying incompressibility. So you're not creating mass out of nothing, but somehow you have a way for trajectories to be at the same place at the same time and separate. And if you think about that, this phenomena is much more unpredictable, much more mixing than chaoticity. Because if you have a chaotic system, so in a chaotic system, the separation at time t is something like initial separation times exponential lambda t, where lambda is the Lyapunov exponent. So chaotic means that you have lambda positive. So here, if you make this to 0 for a finite time, for a fixed time, you make initial separation to 0. Basically, the final separation is going to 0 also. Here, in this spontaneous stochastic scenario, what you have is that even if you make separation equal to 0, you can get a finite separation over a finite time. Okay, so which means that its mixing is infinitely more efficient than in chaotic flow. So now this, yes.
The plot, like, so you started to, this is an ensemble of trajectories.
Yes, exactly. So that's a sketch coming from a one-dimensional model where you put some Ross function here, and basically you let things develop for a very tiny value of the diffusivity.
Okay.
Okay.
So these trajectories with are like, so this plot that you are showing.
This one?
Yeah.
Yes.
So this is an evolution of this equation, right? Dx by dt is equals to
Exactly. It's a one-dimensional model for that, where U is some model which is Ross with respect to x, so which has some exponent less than 1 here, and maybe I think it's white noise in time. So it's white noise in times with some h for the spatial independence, and here what you do is that you start from initial conditions which are all here, okay, and you let these different initial conditions evolve with different values of kappa, which are very, 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 very small, which are much smaller than the diffusion, I mean the dispersion that you observe on the figure. So the fact that this thing is leading to a big set of trajectories is mainly due to the fact that you have this kind of properties of the flow.
So if h was 2, then you would get like.
If h is 2, I'm in that case. Now, if h is 1, if h is 1 or larger,
yeah,
I'm in the chaotic case. H cannot be more than 1 actually, because you see, if your flow is differentiable, then this thing is of the order of 1. So to make it bigger than 1, so for instance, if you want a parabola, etc., basically this can be only in one position, in one point in space. But this is true for all points. See?
So is this U is not random here, right?
U is no. In this case, U is random. In this case, U is for this case, it's a one-dimensional version of the Crichton model.
Brownian motion.
I didn't check.
It's a Brownian motion, right?
It's
but he is not.
So let me write this thing here.
Brownian motion, there's no x dependence.
So this specific case will be a solution to the following equation. okay? And U of X is Gaussian, is a Gaussian process with zero mean and with correlation. So it's white noise in space. So it will be something like, so some constant times 1 minus, let me write it this way. So it's as a D0 minus D1 times X minus X prime to some power 2H times delta correlated in time. Okay? And then here I have chosen H less than 1. So practically how one is doing, so one is not exactly generating this thing. So one is generating a field. So for instance, via Fourier transform, so you generate the Fourier transform of that. So this Fourier transform, you have a cutoff. So which means that at the end, at very small scales, you don't have that anymore, but it's smooth at small scales. And since it's smooth at small scales, basically it's as if you had a regularization at small scales. And the idea now is to make this regularization to 0, and at the same time, this noise here to 0. So this is why you have this double limit. So this is noise diffusion to 0, and this is like the regularization of the small scales of your flow. So you make the two go to 0, and then what you get is that the probability of having two different positions, knowing that you started from the same, is different from having these two final positions equal. No, if you make diffusion to 0, no.
Yeah, because U is random. So even if I start.
Yeah, but if it's smooth, if U is Lipschitz, so if H is 1, for instance, then this thing will tend to that. Then it's just if this thing is smooth, you just have a classical ordinary differential equation to which you're adding noise, and when you make noise to 0, basically you converge to the solution of the ODE without the stochastic term. Yes, so yes, but assume that you okay, I'm sorry. So this P2 here is not an average. There is no average with respect to U.
It's for one realization of
yes.
U.
So let me yeah, exactly. So it was. Oh, I'm sorry, I'm going the wrong way. So here, yes, maybe here I was not clear enough. Is that this average here is with respect to kappa, to this noise only. I should have put the eta or kappa here.
So you're saying.
So you fix a realization of U. Okay, realization of U is fixed. There is no average with respect to realization of U.
So for one particular realization also, it's not same.
Yes, exactly.
H is less than 1.
Exactly.
Because of this non-uniqueness.
Because of this non-uniqueness.
Because of this condition.
Yes, because of this non-Lipschitz character. Okay, so now let's think a bit more about the so again I have epsilon theta with a minus, so it should be plus. I'm sorry. So basically now this character, this non-uniqueness character, it explains the fact that for the passive scalar we have a dissipative anomaly. So remember how you write the scalar dissipation. So it's with a plus again. And so now what we know is that, so what we can show is that this scalar dissipation is going to a constant when you make both diffusivity and viscosity to 0 by fixing the Prandtl number, which is the ratio between the two. So you fix the ratio between the two, you make the viscosity and diffusivity to 0, and then you maintain a finite dissipation of the scalar field. So why you do that? So you go back to this formulation here, okay? But now you write it for theta square, so our scalar energy. And if you write it for the scalar energy, so now what you get is that somehow the probability of transition, so time derivative is just acting on that, on P2. And so the scalar fluctuations are related to initial correlations at 2 different points times the probability of starting from these 2 points, finishing at the same point. Okay, so the thing which is different from before is just that here I have taken r equal to 0. So r equal to 0 means that here I have to finish at the same point. I'm sorry, it should be this condition on that, and to be consistent with what I wrote before. Okay, but in incompressible flow, it doesn't mind on which side you're conditioning. So it's a detail. And so the thing which is important is that somehow it's what you need to have non-unique in order to get scalar dissipation is the backward flow. So you have to be able to bring at the same position different trajectories, which are bringing with them different values of the scalar field. And this, so now if you look at the simulation of a scalar field, so this is a scalar field transported by 3D Navier-Stokes. So the different colors are different values of the scalar field. And so having a finite probability to finish at the same position, knowing that you started from different positions, here is you can see it through the presence of these fronts. Okay, so you have position in space where the scalar is having almost a discontinuity. And this is the place where you get the max of dissipation of the scalar field. So maybe I can rewind to this figure that I didn't comment actually. So this is again a scalar field which is transported by a 3D turbulent flow. It's 3D, but now I've taken a slice of this 3-dimensional flow. And again, you see that you have positions with a variation which is very, very sharp between red and yellow. There, here also. And this is the place where dissipation is taking place. So I mean, you see it a bit from these figures. It's not that. So for instance, you see it from here. So here you have a sharp thing. Here you see that the dissipation is very strong. So this is the dissipation of the scalar field at the same time, in the same slice. Okay, so you see that Lagrangian, the fact that the Lagrangian flow is ill-defined, has this non-uniqueness of Lagrangian trajectories, is explaining anomalous scaling and dissipative anomaly. So now I want to give a bit more details on what's happening on a part of what is done in order to investigate a bit the Lagrangian properties of the flow and to focus on pair dispersion in the developed turbulent flow. And so now I'm looking at the statistics of how pairs of particles are behaving as a function of time. Okay, and basically, so which means that I want to understand better this kind of probabilities. Okay, and so the thing is that now I'm looking at the evolution of the distance between two tracers, and I'm fixing their initial separation to be some R0. And now when I'm writing these things, I want to do statistics with respect to the fluid. of the separation of this thing conditioned on this initial distance. Because this is the kind of statistics I want to do. So typically for this the time evolution of this distance, there are two regimes. So the first regime, which is called the bachelor regime, so which dates back from this work by Bachelor, is what's happening on very short time scales. It's on very short time scales. So I have a finite separation between the trajectories. So what I have is that since the trajectories are at two different positions, they have different velocities. Since they have different velocities, they will start to separate ballistically with a velocity which is given by the difference of their velocities. So if I just Taylor expand the separation, so the separation at time t will be initial separation plus t times the increment of velocity between these 2 points, these two initial points. And then I have subleading terms which are corresponding to the increment of the fluid acceleration between these 2 points. Okay, so what I call delta U, you see, is the initial increment at time 0. So at time 0 is the reference time where I fix the separation. And what I call the acceleration is this acceleration, of course, the material derivative of the velocity. So now if I use this thing and compute the mean square increment of the separation between particles. So I take their separation time t minus their initial separation squared, and I make an average with respect to all the different R0s I have, all the different pairs which are separated by R0. So then I just plug that here in this thing. And what I get is that I have two terms. So one which is proportional to t square times the second order structure function of my velocity field. And another one which is like t cube times this delta u dot increment of the acceleration. So now let me assume K41. So if I assume K41, this S2, I can write it as epsilon R0 to the 2/3. Okay. Then this term here, which is the scalar product between increment of velocity, I'm sorry, there is a delta missing here, and increment of the acceleration, I can write it this way, and basically it's just 1/2 of the time derivative of the square of the square increment, of the increment of order 2, structure function of order 2, and this is nothing but -2 times energy dissipation. I mean, this is a consequence actually of Navier-Stokes. So now, which means that I can write exactly this term and this term, and so I can compute the time at which my ballistic regime is finishing. So ballistic regime will finish when, so ballistic regime corresponds to having this dominant. Okay, so R square is like T square. And now this ballistic regime will end up at a time shorter than the time at which this thing is becoming larger than that. So when my expansion is fading. So now if I balance these two terms, what I get is that I get this crossover time between ballistic and what's happening later. And this crossover time, you see, I can rewrite it this way. It's nothing but the turnover time at my initial scale. So let me summarize this thing. So initially, you take two tracers separated by R0, and you look how they separate in an initial regime. So initially, they just separate ballistically, and they separate ballistically with a velocity which is the typical velocity that they had at initial time, at initial separation R0, the typical velocity increment at this separation R0. And this, they do it for a time which is like the turnover time associated to this scale R0. Okay? So this is the first regime. Next regime is what we call the Richardson separation. So once they have gone far enough then there is a signature of this non-uniqueness that we have in the flow. So what is this thing? So basically, now if we are looking at time larger than this initial, than the length of this, the time length of this initial ballistic regime. So what we have is that we can now say that typically the time derivative of the separation between the particles is like the increment of velocity at this very specific value of the separation. And this you approximate it using Kolmogorov 1941, so it's like r to the 1/3. Now you look, so basically it's more or less the equation I wrote before. Okay, like dr dt is proportional to r to the 1/3. And so what you get is that you have this explosive regime. It's called explosive regime or Richardson law, where the square separation condition on this R0 is growing like T cube. So it's super diffusive. Okay, it's faster than T. It would be T if it was diffusive. So it's T cube, it's explosive, very, very, very fast. And then the thing that is a signature of this non-uniqueness is that the coefficient that you have in front, this G epsilon, so G is a constant, epsilon is the rate of energy dissipation, is independent of R0. Okay, so independently of R0, at some point, so after this T0, so T0 depends on R0, then my particle will just start to separate in this super diffusive regime. Okay. So, I mean, it's almost 100 years, or so 1926. Richardson proposed this law based on observation. So he was measuring, so he did measurements in the atmosphere. He was launching balloons, and he was measuring by eye the distance between balloons as a function of time. And then from that, he got this kind of law, which is a bit amazing. And then, so basically, this was more or less formalized by Obukhov, 1941, which is let's say what's the name of this magic year for Einstein? Is the year where he did everything. I don't remember, but what? Yes, yes. So Annus Nobilis or Mirabilis. Okay. So 1941 is so I don't know how we would say it in Russian, but it's the Annus Mirabilis of turbulence in Russia. But Obukhov was very close to Kolmogorov. I mean, basically he was not a student, but he was more or less in next office or something like this. So basically he formalized it and really wrote this law. So it's called the Richardson-Obukhov law. And so now again, as in the case of velocity increments, basically since you have some scaling between r square and t, r and t. So r is going like t to the 3/2. Basically, you can maybe pretend to write that there will be some scaling regime this way, where the 2-point probability transition probability of the separation, okay, will just be a function of r divided by t to the 3/2.
So,
yes.
Like this, if you had one balloon,
yes,
and like you look at r square, that will go as t, right? Because
yeah, sure. This is the no. It will go like t. It will go like t only if you look at very long times.
So this will eventually go as t.
No. Yes, this also will also go like t at very long times. And in order for one balloon to go also diffusive, you need to wait very long time. So this was the first thing, the Taylor diffusion. Taylor diffusion. So it's if you are looking at one particle somehow, see, and then you need to wait a time which is longer than the Lagrangian correlation time of the flow. Then it's becoming diffusive.
Okay, even for a single guy.
Even for a single thing.
Okay. So initially you see it's still T cube or
yes, and the diffusion is given by the turbulent diffusion.
Right.
for one thing.
But that is a very long time.
And this is a very long time. And here for two things. So of course, if you go to times which are larger than the Lagrangian correlation time,
Okay.
then of course things are getting uncorrelated, and again you will retrieve the diffusion.
And the other question was, so earlier you showed if you take two initial conditions, they get separated exponentially, right?
If they are
Two different initial conditions.
yes, but if the initial separation is small also.
It was only for very small initial.
Yeah, because in order to get the exponential thing, so where is it? It's
Before the,
or here in this equation. In order to get the exponential stuff, you need to be able to linearize this thing.
So that is even at.
So it's so this means that you need to choose your R0, your initial separation, at very, very small scales. So here we are, R0 is arbitrary, is in the inertial range. Okay. So now this is more or less how the picture is looking like. So initially, so you start, so I'm sorry, R0 should be there. Okay. So you start with some R0, which is very small. You first have this ballistic thing, which bring you to twice more or less the separation that you had initially. And then, so this is more like the time t0. I don't know why this R0 is here. Then you have this explosive thing where everything is, where R square is going like t cube. Okay. So of course, the problem is the following: is that in order to observe this law, it's pretty difficult in both experiments and numerical simulations because you need very huge scale separations. So you need. First, you need time to be much less than the large scale, of course, because otherwise you have a simple diffusion. Then you need this time to be bigger than the end of your ballistic regime. Okay, and then you also need this time for the ballistic regime to be much larger than the Kolmogorov time, the small scale. So you see, you need maybe a factor 1,000 between tau eta and tau L in order to see something. At least 1,000. So this is more or less the state of the art of what we observe here. So basically, this is R of t minus R0 squared. So it's normalized the proper way here in terms of T0, here in terms of this initial ballistic regime, such that initially, so then the different symbols are different R0s, larger than eta, larger than inside the inertial range, and such that, so it's normalized in such a way that both the ballistic regime, which is this dashed line here, is collapsing, and the explosive regime, which is this cube line here, is also collapsing. So you see that indeed you observe at least, so for the circles, you see that you have some deviations here. But for as soon as you go far enough in the inertial range, you see that you have these two regimes which are developing. Okay. So now, there is now that we know a bit what is the scaling. So there are different ways to try to model this pair dispersion. So one which is called Richardson diffusion. So actually, the work of Richardson, the fact that he was measuring balloons like that, was in order to estimate diffusion coefficients to put in an equation for P2. So imagine that you want the transition probability like that. So you want to write it as a diffusion equation this way. So, but then you don't know what to put as a diffusion coefficient. So what Richardson made, he measured this separation of balloons in order to estimate this diffusion coefficient. And so basically what he got is something which is proportional to this R to the 4/3, okay, by this measurement. But he didn't make the link between this 4/3 power he was measuring and anything happening in the flow. See, so Richardson, it was in 1926. The first person who said, the velocity is like R to the 1/3 was Kolmogorov in 1941. Okay, so almost 20 years later. 15 years later. So now, if you, so Obukhov was the person who made the link between the two. in 1941. And basically, so which means that now you can say, thanks to Obukhov, that you have to write it this way. Okay. And now if you put this here, in this, so if you put this scaling here, so then you get a solution to this Richardson diffusion model that is so it's an asymptotic solution at large times, and it has the scaling form I was talking about before, and is indeed implying that the R square is going like T cube. So now, in the case of the Crichton model, so the case with a Gaussian velocity field, advection by Gaussian velocity field with correlations which are this way. Okay, so it's basically what I wrote before. You see, so here, yeah, it's even the D0 and the D1 were almost to write the same notations. So Crichton model. So you have correlation of velocities are delta, data correlated in time. Then you have a specific form, and this specific form, the part which is depending on the separation, you see, is going like R to some power xi, and xi is 2h, okay, in our language. So now, basically, in this case, you can formalize, for this kind of flow, you can formalize the fact that the 2-point transition probability is following such a law. Okay, so for Crichton model, you can show that indeed you have this scaling form for the 2-point transition probability at long times. So Richardson works in Crichton model. The problem of this approach, see, is the following: is that so now here what you want to say, phenomenologically, what you want to say is that you basically at each time step, your velocity difference is like R to the 1/3, but it's independent of what happened at the previous time step. Okay, so this is the white noise thing. So which will mean that you will need to coarse grain on times which are longer than the correlation time associated to your velocity at a given scale R. So the problem is that the correlation time at a given scale R is like R to the 2/3. Okay, so this is the usual turbulent scaling. So which means that you need to be able to coarse grain at each scale on the time which is longer than R to the 2/3. But at the same time, R square is going like T cube because of that. So which means that the correlation time of your flow is actually of the same order as T. So you want to have a model which is effective up to time T, but actually at time T, you had only one correlation time. So you cannot rely on averaging over a large number of correlation times in order to build a diffusive model. Okay, so basically, there is some inconsistency between writing this thing and finite correlation times in a turbulent flow. And the only way one can really formalize this thing is by assuming delta correlation in time in the Crichton model. So if you are delta correlating in time, as in the Crichton model, of course you don't have this problem. Okay, so just to finish, so now if you compare actual data to the Richardson distribution, so Richardson distribution, remember, is this scaling form. So you do some massage. So you represent R divided by its variance, by its standard deviation to the power 2/3. And here you multiply P of R by this factor and divide by R square. So that at the end, if this distribution in these variables is just the dashed line. Okay, so it will be just the dashed line. So now what you see is that data, they deviate at small separations. So you have broader tails, so you have a larger probability for particles to remain closer than with the Richardson diffusion. And then you have a very sensitive dependence on the other tail, very sensitive dependence on the initial separation, which means that maybe there is some memory of the initial separation of R0, which is going further in time when you look at large separations. And of course, what makes Richardson distribution pretty nice as a model is that you see that you have these 2 points where everything is pinched. So which means that, of course, if you pinch here and pinch here, I mean, the core of the distribution, which is somewhere here, everything looks flat and collapsing to the right curve. Okay, so basically, you see, the thing is that, that's what I wrote here, is that this is a bit cheating by doing that, because, of course, you do everything so that the core of the distribution is collapsing. So, of course, the core is well represented by Richardson distribution. So I will stop here, already late. Some questions, 1 or 2 short questions, or you prefer coffee? Online?
Online, any questions?